Welcome folks to the first module from the Microsoft Flight Simulator 2024 Detailed A320 course. Throughout this course we will cover everything, from how to read charts to the different type of hydraulic systems that are on board a A320. My goal and the final module will be to complete a full flight using all the procedures we have just learned. Now I've tried to make this as comprehensive as possible. I've used manuals, real-world procedures, and documentation to give you all the most realistic sim experience for the A320. I'm using the Phoenix version of this aircraft, but most of the procedures should be applicable to any high-level sim A320. So let's kick off the first module here with preliminary cockpit preparation. Here we go. Now before we step into the cockpit for the preliminary preparation, we do a safety exterior inspection. Just bear in mind it's different to a walk around. A walk around is a methodical, detailed look at the aircraft from the exterior, whereas a safety exterior inspection is only looking at a few things. And those things are the wheel chocks in place? What is the condition of the landing gear doors? And how does the APU area look? Once we have completed this safety exterior inspection, we can then begin the preliminary cockpit preparation. Okay, so there are three main objectives of the preliminary cockpit preparation. The first is to ensure that all safety checks are performed before we apply electrical power to the aircraft. The second is to check the liquid levels, that is the oil, hydraulic, and oxygen pressure levels. And the third is to check the position of any surface control levers, i.e. slats, flaps, and parking brakes. It's also important to mention that any flight crew must review all the OEBs or Operations Engineering Bulletins applicable to that aircraft, with particular attention being paid to the red OEBs. Okay, so as we make our way into the captain's chair in this cold and dark aircraft, there are particular flows that we need to follow for the preliminary cockpit preparation. And we start those flows in what's known as the center pedestal. It's a really efficient design that gives flight crew access to multiple system controls in one area. Within the center pedestal, we're going to first focus on engine master switches 1 and 2 both off. Next, engine mode selector set to norm. The next area we check is the weather radar panel. The radar set to off. The wind shear is set to off. The gain knob is usually set to cal, but within this aircraft the Phoenix has it preset at +4. And the mode is set to weather and turbulence. We'll go through the weather radar in a little more detail in a later module. Lastly, in this section, we check the parking brake is set to on and the landing gear lever is down. Once our center pedestal flow is completed, we then move to our overhead panel where we check that the wipers are set to off. Airbus designed this overhead panel to be super intuitive and user-friendly. It's organized in a very logical manner and is broken into several different sections. The first section we're going to focus on is the electrical power distribution panel. The electrical power system consists of two segments. The first, a 3-phase constant frequency AC system, and the second is a 28-volt DC system. The electrical system has 2 engine-driven generators and 1 APU generator, and each generator can provide AC power to all of the electrical buses. For the DC power generation, there are 2 main batteries, each with a normal capacity of 23 amp hours. If the aircraft has not been electrically supplied for 6 hours or more, you must check the battery's voltage, BAT 1 and 2, are above 25.5 volts. If it's less than 25.5 volts, then a charging cycle of approximately 20 minutes will be needed. However, in this scenario, it is above 25.5 volts, so we can go ahead and turn on batteries 1 and 2. We can see that external power is available via the ground power unit, so we'll switch this on as well. As the aircraft comes to life and the system relays switch on and are self-tested, I did want to talk a little bit about the priority logic of the electrical systems and which source can be used when. First are the engine generators, followed by external power, the APU generator, ram turbine, and finally the batteries. So for example, if the aircraft is supplied by the APU generator and then the external power comes online, the system will automatically switch to external power. However, when the engine gen comes online, the system will automatically switch to that engine gen. And this priority logic is very important when it comes to system failures and emergency procedures as well. Okay, we have our chimes and clicks for self-test completion. Let's go overhead to perform our APU fire test. We first check that the push button is in and guarded, and we check that the agent light is off. When pressed, a continuous repetitive chime sounds, the master warn light flashes, and the APU fire warning appears on the ECAM. The squib light comes on white if supplies are available, and the discharge light comes on amber. The APU, or the auxiliary power unit, is an important part of the Airbus A320 functionality. It's a small but powerful system that's responsible for providing electrical power and compressed air to various systems on the aircraft. It's a self-contained unit located in the tail of the aircraft, and it serves as an independent source of power for essential functions that can be performed even when the main engines are not running. When to start the APU is dependent on airline and airport restrictions and procedures. It's really dependent on things like unnecessary fuel burns, environmental impact, and air conditioning necessity. To start the APU, we press the master switch to on, wait 3 seconds, and then press the start switch. This is to avoid any spurious errors that may come up on the ECAM that can require shutdown and maintenance. As the APU air intake flap is open, the electrical power shifts to the APU system. The APU fuel isolation valve opens, and if there's no fuel tank pump running, then the APU fuel pump will operate itself. We see a rise in exhaust gas temperature and an increase in APU fan speed. This is an important process, and it should be completed in full prior to any other systems being started. Okay, we have our avail message on our lower ECAM, and we have the avail message on our upper ECAM. We are ready to start our bleed system. Now it's called bleed air because pressure is essentially bled from that compressor section of the engine and the APU. It's used for engine start, pressurization, air conditioning, and anti-ice. Now we first check that there is no pressure in the bleed system. Then we check that the cross bleed is on auto, and we start the bleed. Now the way the air conditioning packs work is they draw outside air, compress it, and mix it with the recirculated cabin air to maintain a selected temperature. For the 3 temperature dials, the range is 18 to 30 with the center notch being 24 degrees centigrade. Standard operating procedures recommend if it's less than 130 passengers, you set the pack flow to low, which is 80% of normal flow and slightly more fuel efficient. And if it's greater than 130 passengers, you set it to norm mode, which is 100% flow. If it's a full plane, you set it to high, which is 120% of normal flow, which gives the plane less fuel efficiency. Now the next step in our flows is aligning the ADIRS, which are the Air Data Inertial Reference System. Now the system comprises of 3 ADIRS, which are Air Data Inertial Reference Units. Each unit has 2 subsequent systems. The first is inertial reference, which provides metrics such as position, attitude, ground speed, and heading. And the second is air data reference, which provides metrics such as barometric altitude, overspeed warnings, angle of attack, airspeed, temperature, and Mach. The ADIRS are set in sequence. Unit 1 is set to nav for the captain, Unit 2 for the first officer, and Unit 3 as a standby. Previously, you had to wait until the on-bat light had appeared and then extinguished before moving on to the next ADIRS. However, now Airbus has put a new process to turn on all knobs consecutively. For the next part of our preparation, we move through the overhead panel flows. We generally follow the Airbus philosophy, which is all white lights out for each phase of the preparation. Firstly, crew supply on, which opens the solenoid valve of the oxygen system. Next, we switch on ground control and test the cockpit voice recorder system. We turn on the strobe light to auto, the nav light to on, which helps with walk around as well. No smoking is set to auto, and we arm the emergency exit lights. Seatbelt sign is set to off as we haven't completed refueling yet. The next step in the preliminary preparation is to observe the aircraft status on the Electronic Centralized Aircraft Monitoring, or ECAM. The upper ECAM display is called the Engine Warning Display. It shows the primary engine parameters, slats and flaps information, fuel on board, warnings and memo messages. The lower ECAM provides the pilots with diagrams of the aircraft systems, status messages, as well as permanent flight data. The SOP flow here is performed using the acronym HOOR: hydraulic, oxygen, oil, and recall. The A320 hydraulic system is comprised of 3 continuously operating systems called yellow, green, and blue systems. Each has its own reservoir and fluid with no fluid transfer from one system to the other. They are completely independent. The power for the green hydraulic system comes from the engine-driven pump on number 1 engine. It's pressurized to 3000 psi. The yellow system is pressurized by engine-driven pump on engine number 2. It can be powered in a number of other ways too. Firstly, by the yellow electric pump, which can be powered on the ground even with engine number 2 shut down. Secondly, it can also be pressurized by a hand pump used by the ground crew to operate the cargo doors when there is no electrical power to the plane. The blue system can be pressurized by the blue electric pump. However, in an emergency, the ram air turbine, or RAT, can supply pressure to the blue system also. The ram air turbine is a cool piece of technology. It's essentially a small propeller that can be deployed into the airstream to supply that hydraulic power to the blue electric system in case of a dual engine failure or even a serious electrical problem. For cockpit preparation, we need to check the hydraulic reservoir fluid levels should be in the green range, as hydraulics have not been powered yet, and once powered, they should then be in the white range. We then move to the door page to check for the cockpit oxygen pressure, which should be greater than 1500 psi. We then check the engine page to make sure the oil quantity is greater than 9.5 quarts. Estimated consumption is roughly 0.5 quarts per hour. Lastly, we press the recall button to check if there were any faults from the previous flight. In this case, it's normal. Before our walk around, there are a few things we need to do while we are still seated. We first check our flight control systems. We check the flap position on the upper ECAM matches the flap lever position. We check the speed brake is retracted and disarmed, and then we check our brake pressures. We test this by turning off the park brake and applying the toe brakes. We make sure that the accumulator pressure is within the green band. If needed, we can use the electrical pump on the yellow hydraulic system to recharge that accumulator pressure. Alternatively, we could even open the starboard cargo door. We then reapply the park brake, which we need for the walk around to check the brake wear indicators. Lastly, as we stand to leave the cockpit for the walk around, we check all of the emergency equipment. We make sure there is a life jacket, smoke hood, gloves, an axe, portable fire extinguisher, oxygen mask, and the escape rope. We check that none of the circuit breakers have popped out, and we leave the cockpit to begin our walk around. In Module 2, we will cover the exterior walk around in full detail. We'll see you then.